Right, hello everyone. Today we're going to be covering, well, every title has to have a really long and fancy title, so I went with the old name Nutrix Backdooring the Linux for this encryption for remote forensic password recovery, because I thought that would get enough people in the room, and I think it might have worked. I know to turn on my hotspot for later. There we go. Okay, so first, the classic hello world. Hello, my name is Tom. You can visit the amazing tomco.com. I've worked in cybersecurity for about 12 years, and this is my third time turning to B-side casing Stoke because I've been informed it's amazing Stoke. I think it is. I've got an MSc in software system security and worked in various firms. I used to have part-time security researcher at the bottom here. I've now put very part-time security researcher because I haven't found a CV in quite a while. Mostly working in editing and writing some creative tools on the weekend. What are we going to be covering here? We're going to be covering lots of different bits and bobs. We're going to be covering the evil mail attack. We can talk about BIOS. We can talk about the Linux boot process for this encryption, trusted platforms. We can put everything together to summarize all of these points. Why are we doing this? Because I think there's lots of cool concepts here by a lot of smart security people who start with me, which isn't particularly common knowledge. I just kind of want to bring all these things up to you, explain to them what they are, why you should care about them, and why all of them have a bunch of weird quirks in them. And as we all know in the security profession, it's the weird quirks that what's actually interesting. So first, refresher, what is the evil mail attack? Raise your hand if you've heard of it before. Okay, so I did pitch this at the right point. Fantastic. So this refers to an attack of a usually powered off unattended device. This is the classic, I lose my laptop on the tube, what can people get away with? The term was coined a very long time ago in a blog called Evil Mail Goes Against TrueCrypt, which is the idea of you leave your TrueCrypt encrypted device in your hotel room. Someone comes in to do maintenance, what can they get away with? And again, it's talking about tampering with BIOS, UEFI, disencryption, etc., which is what we're going to talk about here. Also, semi-related is the cold boot attack. Raise your hand if you've heard of that one. Yeah, it's the same hands again. So this is talking about how an device is running, but fully encrypted, and you spray them down with RAM chips to get them really cold, and you can pull them out, put them on a separate device to do that, and upgrade them and decrypt it. Cool. So, this is my laptop. I'm on lunch. Please do not tamper with it. But of course, we're talking about a device that is powered off, so that's better. This is the kind of device that we're going to be talking about today. So, refresher, BIOS, the basic in and out of the system. We all kind of know this, but just to highlight the series of steps that you need to go through to turn on the computer. Pushing the power button, going through the boot process, initializing hardware, going looking at your master boot record, bootloader, config, kernel. I put here a really initial RAM file system with a star because this is more of a Linux thing than a Windows thing, but this boot process is kind of what we're all familiar with. Raise your hand if you're not familiar with this. Okay, good. So BIOS is kind of dead. We've got UEFI, which is the new thing. Who knows what it stands for? It stands for Unicorn Enchanted Fairy Interface, because no one seems to really know what it is. Everyone just kind of switched over to it. Hopefully when you walk away from this talk, you'll know that it stands for the Unified Extensible Firmware Interface, and hopefully some more things. So how does the boot process change? So instead of booting into BIOS, you boot into UEFI. And instead of having to search the hard drive for a master boot record, which is of a specific size right at the start of the disk, we now have support for the FAT file system, FAT16 and FAT32, I believe. So now with the UEFI, you can actually read that file system on the disk, and we'll go off to a piece of hardware called your AV-RAM to understand what things it's trying to look for in that FAT file system. And then instead of reading a bootloader of set size, you have these things called EFI executables, which are your traditional bootloader. It can also be a shell, it can be a recovery thing, it can be a Mentos application. And then we go through the normal boot process. So with that in mind, if someone has physical access to your computer, what can they tamper with? So first we're going to highlight those kind of two sections of this. There's the firmware side, and there's everything on the disk. And these are things that they can't really tamper with, really. Power button initialization is more just a general process. But these are all things that they can tamper with, which is a fair amount. So we need to think about how we're going to secure this. And really, the first thing we're going to talk about is securing everything on disk. So, how we protect disk? Full disk encryption. Who here has full disk encryption in their business and in their enterprise? I was hoping for a lot more hands. Okay, so let's talk about that. We've got Windows, we've got BitLocker, we've got Mac with FileVault and T2, and we have self-encryption drives with the open standard. As with all of them, they're all a bit weird. BitLocker for Windows we're going to touch on. If you're using a Mac with the T2 chip, your device is encrypted out of the box. And if you read the hardware specification for the T2 chip, we're very interested in kind of logarithmic curve about how many password attempts you can make. And after a certain point, the standard just says after 150 password attempts, the T2 chip will just refuse to work anymore, which is an interesting security feature. And self-encryption drives you see a lot in data centers. We're going to talk about Linux with crypto setup, Lux disk encryption, TM encryption, and so Linux, Lux stands for Linux Unified Key Setup. It's a standard for disk encryption. The V2 supports JSON metadata. There's one master encryption key for Lux for the entire disk, and there's 7 different key slots, which is a nice thing because what you can do is you can have up to 8 different passwords or ways to unlock a Lux device. So you don't have to remember them. It also has a thing called network-enabled encryption, which is something in Red Hat devices, where you can make the device automatically unlock itself when it's present on the network. And then when you move from that network, like taking outside your corporate, it refuses to boot, which is a really nice thing for corporate devices. And also having different passwords, so that's nice. It also has a concept called anti-forensic striping, which is when the password is split into different crypto data is split into different chunks on the hard disk. So when you try to erase it through like a secure erase process or put those zeros, it makes it harder to, if that erase process doesn't complete successfully or only gets halfway, it still means that most or enough of the key material is destroyed. The one thing I really want to highlight in this is that encryption key is only generated at the device's creation. It is never changed, it's never rotated, and it's actually very difficult to attempt to rotate it, which we're going to touch on later on in this presentation. Here's an example of my laptop. You can see it's using AS, it's using XGS encryption mode. You can see the 2 key slots available. You can see the ones at the bottom that are currently disabled. And I've blurred everything out, so I don't want to show you my encryption keys. Cool. So, who here thinks full disk encryption encrypts the whole disk? Yes, it doesn't. Which is what I want to kind of highlight here, which is just a very strange quirk of. So this is an Endeavour OS install. You can see as it highlighted by gparted that the full disk in this case is actually encrypted. Slash is my encrypted swap, and it's an unallocated space. This is because for Arch-facing solutions, we encrypt the whole disk, and the bootloader, which in this case is Grub, has support to read Lux devices. And then it's actually, rather than just understanding that disk, unlocking it and then reading the Linux kernel and then executing it and then continuing on with the boot process. However, for most other Linux installs, which in this case I'm talking about Ubuntu-based systems, Linux Mint, they don't do this. They only apply the Lux encryption on the root volume group with the boot sector for EFI and your Linux kernel. And the file system are left unlocked and accessible at all times. This is a very common approach. This demonstration is going to talk specifically about Linux Unity because just as a common one, but this is also the same thing that happened with Linux systems. And I recommend that if you are using full encryption for your sake, this is something I would look at. Refresher, the init RAM file system is the init RAM file system. It uses the CPIO format. It's actually very strange. It's 3 CPIO bundled packages all stuck together, and then only one of them is compressed. And if you run it through bin warp, you'll find that it doesn't quite understand what's going on. And there's a lot of fun discussion. If you're bored and have some time to read this is something to Google. Why does it use the file system? Basically, the creator at the time said, I never, ever, ever want to see tar in Linux in the kernel source code. Please no, can you do something else? So they said that CPIO has a nicer file format and be more appropriate and easier to implement. It contains it's a file system containing a bunch of small tools you need to initialize other devices that are connected, initialize your root device before the mounting process is passed over to your system. Installation scripts and binaries. Also contains like a little splash screen, fancy animations, and uses set up RAID devices. But most importantly, it can be used to ask for your disk encryption passwords and then unlock that device, which is one of its primary uses. Cool, so we've implemented full disk encryption successfully, so we can tick that off the list. We can now talk about protecting firmware. So trusted computing, TPM is trusted. There's 2 versions, 1.2 and 2.0. You've probably seen the Windows 11 specification. Microsoft is very heavily pushing TPM platform because it acts as a root of trust, and as we talk later in these slides, can provide you some very good security assurances about booting your device securely. Interestingly, it has been described as a hardware solution for a software problem, which is something that I would keep in mind for this. It is designed, you should not think of it as a piece of hardware. You should think of it as another software application that is running in a trusted environment, which just happens to be running a piece of hardware usually. So root of trust is a similar device and can't be handled by software, which is part of its design, it's storage. This is not a hardware security module, and we're going to talk a little bit more about that. So things to highlight it is not a hardware security module. Yes, these things can store crypto keys very securely, more securely than probably on the hard disk. But if you really want to get things off a TPM chip, you can. If you're going to store crypto keys for your entire estate, then you want a hardware security module. It uses what is the low pin count bus or SPI in order to communicate to the CPU. These are not secure interfaces. The TPM 1.2 standard basically says, I will talk in plain text over these wires, and as you will see in the next slide, you can grab any encryption keys, any data off these wires very easily. The 2.0 standard does have a little bit of a key exchange between the TPM and the CPU. You set up a secure line for those to transfer, but this is an important quirk that you should keep in mind. You can also get TPMs in firmware like this. You can also get them embedded within your CPU, which in those cases there are not any wires that you can pick data off, so these are considered the more secure options. However, those are made by Intel and AMD. Whether you trust them in their CPUs is another option. Maybe you want to get an Infineon TPM, and then the question is, do you trust Infineon? And I don't know if you remember, but a while ago, I believe it's Infineon that manufactured the chips for all of the UBPs had a quirk in their RSA key generation algorithm, which invalidated every UBP for a short period, and then they have to get reissued. So, always check the suppliers. Hardware solution to solve the problem. So there's a particular video I recommend you looking at by Smash Stacking, which is very good, which is basically saying in 37 seconds, with the right equipment and the right tools, you can just a standard off-the-shelf laptop encryption piece off us and take a fully encrypted BitLocker laptop from being fully encrypted to not being fully encrypted. This is how BitLocker is configured by Microsoft by default on every device with a TPM-only protection. And if you scroll all the way to the bottom of Microsoft documentation, they're saying a very, very, very skilled attacker would be able to bypass this protection in this particular manner. It's not that hard. These tools are commonly available. This is something I want to highlight. If you want to protect this, you can use CPM plus PIN. So if you turn on your computer, you have to enter a PIN which is sent to the CPM for verification, validated, and then encryption piece of this. Or, as I mentioned, use TPM that's built into the CPU. Next up, PCR values, known as the Platform Configuration Register. These are little sections of TPM which you can send data to and basically implements a SHA-1 hash. So that's the current one, the new data is sending and generates a new one. They can't be reset. There are bits in certification you can, and they're designed to not be reset. And they're designed to store different states. And what it means is you can ask the TPM to say, hey, can you assert to me cryptographically the values of your PCR registers? And over the network, you can verify that digital signature to confirm the state of the TPM. And the things that you could be measuring with those TPMs are firmware and kernels. So you have a secure chip in your computer that can't be tampered with. You can get that to store these particular values, which are measurements of various systems like firmware, like your kernel version of your computer, and you can assert cryptographically the values of those. So this is supported by System D, is highlighted in this at the moment. But this is the idea of the beginnings of secure boot, the idea that your TPM can write down the current status of these devices and then securely provide digital signature of that. And then what you can also do, as an extra layer of this, is you can take your piece of information and you can tell the TPM to seal it, to encrypt that against the value of these PCR values. And the practical upshot of that means that you can take something like the encryption password, seal it inside the TPM, and say to the TPM, only unlock this encryption password when I have confirmed all the firmware and all the state of the system is correct and hasn't been tampered with. And this is the fundamentals behind secure boot. Cool. So let's kind of put this all together. So in a perfect world, and in most cases, how does the boot process work? So it's turn on the computer, motherboard starts up, TPM comes online, PCR value set to 0, everything is fine. The hardware is initialized, TPM reads the firmware and sends that to the TPM and says, okay, here it is, it generates a SHA value for it. Boot process happens at UEFI, loads the config file, and then reads whatever UEFI binary you want to boot, Windows bootloader, and also sends that to the TPM, updates the PCR value. You can then check the digital signature of that binary, confirm that it hasn't been tampered with. Then you run it, update TPM again, and then you take the measurements of the kernel and system D sub and the underground file system. So that's the TPM update the counter. And then finally, when you're now booting your operating system, you can say, okay, I need that disencryption password. And TPM will say, okay, all of my PCR values are set to these particular points. These are valid. I will unblock it, I'll send it to you, and then you can boot your operating system. And it's all secure. And then if any points of these you tamper with, you change the PCR values, and then the system will boot. It's pretty cool. How does it work in the real world? In the real world, things are a little bit more messy. If you're running, well, no, a lot of cases, secure boot is just turned off on a lot of people's laptops because depending on what you're running. the way it stands is everything is heavily favoured towards Microsoft. Microsoft only wants to complete signing keys for this. They are shared with other companies, and you can go through the process to implement your own or put them in your own computer, but usually you buy a laptop off the shelf. It's going to be configured for Microsoft, security is going to be enabled. For Linux, there's this very interesting tool called the Shim, which is made by Red Hat, which is signed by Red Hat and by Microsoft. And what this basically means is you can complete the full boot process as normal until you get to the Shim, and then the Shim will then just execute any arbitrary EFI binary you want, which is usually run, and then go through the normal boot process with the kernel, the file system, everything else. So this is kind of where things start to break down. So that in-around file system, I've mentioned it quite a few times. I've just told you that it's not protected by the boot load process. So it's a very good target for a threat actor. How can you backdoor it? Well, we can just walk into to somewhere where the laptop is turned off. We can plug in some kind of memory stick. We can boot off that. We should then mount the underlying disk, pull apart the in-around file system, change a bunch of those files on the disk, slam it all back together. Take about 30 seconds, and the process will look like something like this. So, first thing you want to do is try and clone the access cards in the room, get into the room, pull out their hard drive. You can use something like Verlander to read their disk in something like the MKS format, plug in that memory stick, boot off it. We're going to imagine that you have imaged this person's computer and you've ripped away with it after doing this process. And we're going to run an automated script which is going to update that in-around file system. So here I am kind of putting it apart. There's a tool for this called Unmake in-around file system, which will pull everything apart for you. We're going to now edit the hook of the in-around file system that deals with the cryptography of the Linux encryption. I like to put this here, which is my current mental state when I was writing this presentation, as a marker to say where I have started making my edits. So now, when I run the boot process, I have this, and then I know, this is where I can start making all of my changes. Can anyone highlight to me what the problem with this piece of code is? Something that might seem a bit suspicious that I've added to it. Does anything look out of place? This is yeah? Yes, there's that one line that I've added just there which says, go and get interactively the distribution password and then save it to temp and then unlock the disk. So this is just, this is a literal bit of bash script that's actually unlocking the disk in the in-around file system. And in this case, I'm just using the password. And next up, we're going to edit the file that basically manages the splash screen. And within that, we're going to have a bunch of stuff. The first thing we're going to do is remount the root file system to make it read-write, so that we can, in the process of booting, access the final disk. We're going to then copy that password that I've just stolen. I'm going to slash it into the root file system as /root password. And then we're going to set up a systemd unit, which is going to cat that password, send it over to my server, and remove it. So we can do this over the network. And then we're going to use this systemd unit called network online. So what this means is, once this is all injected into the system, systemd will just wait for your computer to have network access before activating this unit, and then restart it. So on a laptop, this is really handy because it just means the next time it comes online, this will activate. And then finally, we add a little hook here to say, hey systemd, I would like you to start this with your multi-user target, which basically means to do this on boot. And we're going to start a netcat listener on some random server, which in this case is mine. And then we're going to wait. So the person will take this laptop away from their hotel room after it's been infected. The next time they type in the password, it was stolen during the boot process, and then we wait for the laptop to have a network connection. And then once it successfully has a network connection, bam, you receive the password. Very secure password. I recommend thinking something a little bit longer, but I love that password dearly. It's not the password for this device, I promise. So now we have the password. We can take that, we have that clone disk that we stole from quite a while ago, and then we can decrypt it and access all the device on there. We don't need access to them, they're out in the world. The interesting thing about this is we can now dump the Lux master encryption key because all you need is any valid password. And because that encryption key never changes, what this means is at a later date, if they change their disk encryption password, or if that key is rotated or revoked, or a laptop is stolen, or you can then just use that master encryption key to access their data. So another thing is just keep in mind that for Lux devices, once they are cracked, they stay cracked. You have to completely re-image the device in order to rotate that encryption key. I'm now going to attempt a live demo. I'm so serious. I'm not running fast right on myself, so I'm hoping it's going to open fast in this. Okay, so I'm starting it at this here on my server. I've typed in the password into the laptop, which I've already gone through all the steps I was trying about everything within around file system. And there it is. Apples. Fantastic. So mitigations from this. Hopefully this is a few of you in the room, some things to consider. The best way to implement against the even attack is to use true full disk encryption with a correctly configured trusted system. macOS has already had this by default across the systems. This is not something really you can concern about. Windows, if you're using BitLocker correctly and you have a couple of different caveats I talked about around TPM, using TPM pins, correctly configuring your BitLocker, and double checking the security on your fleet, this is also less of a concern. For Linux, all of this is natively supported. You can see here for University B secure boots to say in this particular case, You can enable these things, it's just not usually set by default out of the box. You'll need to go through some human software to enable this, maybe it's worth it. You can also, as a very quick fix, you can set UEFI passwords, so this prevents someone from just opening your laptop, plugging in and then sending a memory stick, and then asking to boot off that memory stick. And then if you really fancy, you can go with a company like Motor Key, and they have a whole system where you can buy one of their laptops, plug in their version of the UEFI into the side of the laptop, and it will go through the whole core boot TPM measurement process, send that to an external Motor Key memory stick, and then that will flash a green light to say the laptop hasn't been tampered with, and then you can continue with the boot process. It's very cool. They've done a lot of work specifically around this problem. Yeah, thank you very much for listening. Any questions?
Yeah.
Yes.
So you made EPS in the cloud.
Yes.
And you've see where this is going. You've put this back in, and you've got your server waiting, and presumably that's all forwarded out. Type of this. Just have like a server that waits to see these passwords and send your laptop. Exactly.
I'm just using Netcat in this case. You could have this as a HTTP endpoint. You could have all of this configured on a memory stick, going to like 13 people's rooms. They're all running in this. You can just read through this process. I'm doing this just for learners, because it's very easy and very hackable, and this is something that's going pretty quickly. But the same can be done on Windows as well if their boot process hasn't been as configured. Any other questions? Yes.
I'm the tolerance to do preparation.
None, Your Honor. Anything else? No. Thank you very much.